And so we have a whole bunch of these partition functions that I could draw up, and I'm just going to write what the partition functions are and not ask you to memorize them or anything like that, but they do look very similar. Okay, so for the electronic, all right, the partition function for the electronic goes as the sum over all quantum number n, principal quantum number, times the degeneracy, and I'm going to use this letter J here for another letter, and that's e raised to the negative beta e sub j. So it looks very similar, right? And there is a degeneracy term for the electronic levels, as we talked about, right, with p orbitals and d orbitals and f orbitals. Those exhibit degeneracy, equivalent energy states. So the vibration, we just did that. So I'll write it again, Q of V, Q for vibration, okay? And that's going to be the sum of all vibrational numbers. And that's going to be no degeneracy terms here, but now that's e to the negative beta. Also, and times eta sub nu. So a very similar form, okay? Our rotational levels look like this, QR, and that's the sum over, this is capital J, which is the rotational quantum number, and we'll get into that in 362. This is my degeneracy term for rotational. It goes 2J plus 1 is like this whole value of G, but still it goes E. What do you want to guess? To the negative beta, right? They're all like the same form of the equation. It's really just a matter of how you calculate the value of energy for those levels. And the only one that's different is the translations, and that goes as V for volume, the volume of the system you're talking about, and this parameter lambda cubed, where lambda is what's called the thermal wavelength, okay? And the thermal wavelength goes as h, Planck's constant, all divided by 2 pi m k Boltzmann t. Okay, so again, we're not going to do much with these other partition functions, but we can use them in a very similar way. And if we want to know information about our total state here, okay, so let's see, how can we write this up? So my total partition function is going to be a product out of all of these. So QR times QT times QV times QE. So we can talk about a total molecular partition function, which is going to give us the population of every single one of these states. It gives us the full picture of the molecule, okay? And of course, the total energy of that system is going to go like, the energy of the translations plus the energy of the rotations plus the energy of the vibrations plus the energy of the electronic transitions. So those energies are additive. The populations are multiplicative, okay? So keep that in mind. This is a good conceptual detail to know, all right? So now, moving forward. So this is where we're going to kind of get into a rather big derivation. And I think that I'm going to turn this derivation of the Maxwell-Boltzmann distribution. So this is going to give us the population of states of translations specifically. I'm going to do this in a third video, okay, because this will be quite a lengthy derivation.